Now, those two examples were for language recognition. We can also use Turing machines for computation. So here's an example again from Rosen's textbook. Construct the Turing machine for adding two non-negative integers. Now, one important detail here is the input numbers will be stored in unary representation. That is the original formulation that when the Turing machine was defined in. So we do not have binary representation using zeros and ones. We just have ones to represent numbers, and however many you have, that is your number. Or rather, since we are working with non-negative integers, 0 is going to be represented by a 1, and the number n is going to be represented by n plus 1 ones. So this is 0, this is 1, this is 2, this is 3, this is 4, and so on. You get the idea. To represent n, where n is a natural number, you use n plus 1 once. So 1 is the only symbol we use to represent the number, and we also have a separator symbol, this star here, the asterisk. Okay, so since we are interested in computing the sum of two numbers, we are going to represent the two numbers using unary, and we are going to separate them using the asterisk. So for instance, consider this input. 1, 1, 1, 1, asterisk 1, 1, 1. So this is the number 3, and this is the number 2. So we are after the sum 3 plus 2 in this representation. So I need a result of 5, and that will be this number, 6 ones, because in unary, that's the number representing 5. Now, how do I do that? I need to get rid of this separator asterisk in between, and I need to also reduce one of the ones, because I have a 1 excess, because each number is represented by n plus 1 ones. So in total, you will have, let's say, this is m, and this is n, and the number of ones here will be n plus 1, and in this one, I will have n plus 1. So in total, I will have n plus 2 ones, but in my result, I need n plus 1 ones. So I need to get rid of one of the ones as well as the separator symbol. And of course, if the first number is 0, represented by just a 1, erasing the 1 and the asterisk is just sufficient. So my alphabet consists of the 0, 1, and the separator symbol. And it turns out that 4 states are sufficient for this operation. And S0 is the initial state. And with an input of 1, and since it cannot be another input because, well, I don't have, this 0 is not present in the alphabet, since the only alternatives are 1 and the separator, and all the numbers are non-negative integers. As you see from this, I have at least a single one. So the first symbol I'm going to encounter for sure is going to be a 1. Therefore, I don't need to specify S0 star as the initial configuration, because it's not going to be encountered anyway. Now, I'm going to take the first one, and I'm actually going to replace it with blank. So that's getting rid of the first one. And I'm going to actually put that instead of the asterisk. But then I'm also going to, I'm going to need to reduce one of the ones. So if in my encounter, in my second input, well, I also change my state to S1 and go right. And in that position, I can either see the separator, the asterisk, or another one. If that is the separator, it means that the first number was 0, which means just erase the separator and you are done, because adding 0 is actually doing nothing. So just take the 0 out, take the separator out, and what remains is the second number anyway, so that is the result. Therefore, if you encounter the separator in the second position, go to S3, which is going to be the final state, and instead of the separator, put a blank, so essentially erase the separator and go right. And as you see, there is no configuration where the state is S3. That's the end of the operation. The machine will halt. So the result is whatever the second number is. That's how you add a number to 0. On the other hand, if the first number is not 0, then you have, obviously, in state S1, your input will be a 1, which means go to a new state S2, okay, and erase this one, because I need to erase one of the ones from this configuration anyway, and go to right, and then search for the separator. I'm in state S2. If I encounter one, don't edit the tape, just move one right until you find the separator. When my state is S2, if I find the separator, simply go to S3, which is the final state, remember, and then instead of this separator, put a 1 and move right. It doesn't really matter whatever you do here, because you are done, because you are going to move to S3, which is the final state, and no configuration is required, is defined with S3, either with an input symbol of 1 or an asterisk. In these quintuples, we don't see S3, so the machine will halt, and the result is going to be found. So for instance, run this on this input. Let me put it here. So recall this is 3, this is 2, and I expect the result to be 5, which is represented by this. So 1, 1, 1, 1, separator, 1, 1, 1. So I'm here with state S0. Okay, so my state will be S1 and put a blank here. So this will be erased simply. And my state will be S1 and go right. So I'm looking here when I'm in state S1. In S1, I have the input as 1. So go to S2 and put a blank instead of this one and move to right. Move to right, I'm looking at this symbol now, I'm in state S2. In S2, if I encounter a 1, do not do anything but move towards right. So move towards right here, again move towards right, because this is also a 1, but now I encounter the separator. So when my state is S2 and the input symbol is the separator, go to state S3, okay, and write a 1 on top of this separator. So instead of this, I'm going to write a 1 here, and I'm going to make a transition into S3. And since I have no quintuple defining the action from state S3 to any other state, the machine halts. And what I have here is, as expected, the representation for number 5.